Now let's begin with rotations. We saw before, translations are not a big deal. And I said, okay, with rotations it will be somehow a little bit more difficult. And it is so. So let's begin to see what about rotations. First, about change or transformations. Let's say it again. Maybe, I hope you remember, we have the beginning pose, and then we have a chain of transformations. These transformations include both. They include translations and rotations. And then at the end, we have our final pose. And then what do we need to do here, or what for is this chain? We have 4 different reasons for this processing. The first one is relative navigation, I think which we are doing very often. And this is, if you know you were here and then you integrate all these changes, all these movements, then you would like to know where are you at the end. The next interesting thing for us is control. We are now here and we would like to be here. Then how to compute which movements we have to do to go from here, this pose to this pose. And then we have the prediction, the predictor. In the predictor is, I know my position now, pose, not only position, and I compute, or I can read my movement speed, rotations and translation. And then I would like to know, if I do nothing, if I change nothing, where will I be in 1 second, in 10 seconds, or in 1 minute? This is the prediction, and this is something like a simulation. And the last point is history. If I was here, or I am here now, and I know which movements I was doing, then I would like to know where I was at the beginning. And these are the 4 reasons why we shall process this chain of transformations. I would like to remember you about translations. You see, you know, translations are not difficult. It's only adding or subtracting coordinates of a 3-dimensional vector. Then how to compute the translation? I am now in position B, and I was before in position A. What occurred? Then the translation vector is not more than the subtraction of vector B minus vector A, and this for all 3 elements of its coordinates. Then we are going to say that is the T for translation from A to B. I can have a chain of such transformations or such translations. And then I have, for example, the translation from, let me see, from A to B, then from B to C, from C to D. And then I will have this beginning position, plus the transformation from A to B, plus the translation from B to C, and the translation for C to D. And a nice thing is, this is permutative. It is only adding. And you know, with adding, it doesn't make a difference what you are adding first and what you are adding later. Therefore, translations are permutative. The result from going to here is the same if you make first this step and this step, or if you make first this step and this step. The result will be the same. And maybe you remember the distance is the root of the square sum of the differences of both the positions, as you know from the school. Okay. But with the rotation, it's not the same. It's not just adding. For example, if we have a rotation in this axis, 90 degrees in this axis, and then 90 degree in this axis, then again 90 degree in this axis, and so just add all rotations in all axes, and then you shall expect the total rotation, but it's not the case. First, to accumulate rotations, we do not add, we multiply. We will see why. And multiplication with vector is not commutative. So it's a difference if you rotate first in a direction and then in the other direction. The result will be something different. You can add rotations only if you are rotating in the same axis. Then you can add first 10 degrees, then 20 degrees, then again 10 degrees, then the results will be 40 degrees on this axis. But if you are rotating in different axes, then you cannot do that anymore, because after every rotation, the other axis will change. And then it's not the same, the 10 degrees in this axis, like the next 10 degrees in the next axis. Let's see an example with an aeroplane. Just a second, please. You can try it. I think you can build your own aeroplane using paper. So build it and try what I am doing now. Let's assume you have this aeroplane, and then you have two rotations. The pitch rotation is in this direction, and the roll rotation is in this direction. So we are going to do two rotations and interchange the sequence. First, remember, roll and pitch. To the top, to the right, if you are the pilot of this aeroplane. Then let's make first the pitch. Then after 90 degrees of pitch, you will be here, and then you roll. You remember? 90 degrees. And this will be your final position. Please remember this. Look into the top, and the right wing looking to you. Okay. Now let's do the same, but first the roll, and then the pitch. Do you know? The result is something totally different. So rotations are not commutative. And something more difficult. Let's assume this is your aeroplane. You know, when rotating in this axis, you are changing your heading, in which direction you are flying. Huh? When rotating in this axis, you are changing your inclination. You are flying to the high or deeper. And if you rotate in this axis here, you are changing your bank. So this is what normally we do to flight curves. And now let's assume this attitude. We are flying so. And now what does it mean to change your heading in this axis? Then it will rotate so. But it's not changing your heading anymore. Your heading was, I am flying in this direction or this direction, but now it's something different. What is doing now? Huh? Exactly the same. If you are changing your roll, it will be the inclination in this direction or in this direction. But now, changing the roll is something totally different. So you can see, you have to be very aware which axis and where are the axes, because after every rotation, the other axis will change too. Okay, sorry, now let's see. Okay, let's come back. This is what I said before. And then we have instruments to measure the rotations. For example, the IMU, Inertial Measurement Unit. And this IMU will measure the rotation in X, Y, and Z. But now we have the nice situation, or the interesting situation. This is fixed to the aeroplane. And when the aeroplane is rotating, then this is rotating too. And then the measurements will be relative to the current position of the aeroplane and not to the position of the ground. So at the beginning, this could be the flight direction, and this could be the vector looking down to the earth. But after flying and some inclinations, it will be something different. Maybe this will not be the direction to the earth anymore, but looking in something in other direction. Okay, maybe you could see it will be permutative if we use a reference frame which is not moving. Let's try. Just a second. I take again my same aeroplane and I make the rotations, again 2 rotations, but now I'm not going to use the reference of the aeroplane. Just a second, please. I'm going to use a fixed reference. Okay, I'm going to define my coordinates like this. So I want to rotate first in this axis and then in this axis, yes? Okay, and this axis, this reference frame will stay constant. Okay, I rotate first on the yellow and then in the red. Remember my position now, yes? Now I rotate first in the red and then in the yellow. Do you see? Now it's looking in other direction. Okay, it is not the reason. They are not interchangeable, they are not permutable. It's not only because the coordinates are rotating together with the aeroplane. It will be the same if you are using an external coordinate frame, reference frame. So it's very tricky. Be very, very aware when handling rotations. You cannot interchange the sequence. But now we have a small problem. only small problem is, if we have this device here, the IMU, it will provide 3 rotations in X, in Y, and in Z. And then you have to compute the total rotation. Then you have to compute how much in each of them and accumulate all of them. Do you remember, it's by multiplication and not by addition. Okay, now which shall we use first and which shall we use last? We are making a sequence, but the reality was not a sequence. The rotations was all 3 axes at the same time. And that is something we cannot compute. So if we are computing first one of these, then the next, we are introducing an error, a computation error. And if the steps are very big, this computation error is going to be very big. Then what we have to do is to do it in very small steps, and with very small steps, the changes of the axis will be very small, and then the error which we're accumulating is very small, like integration. When you are integrating using very small steps, your accumulation of error will be very small. Excuse me, please. I was mentioning we have to accumulate the rotations. Even if all these rotations occur at the same time, in our computations we have to do a sequence. Then which shall we compute first, then next, and then next? In any case, we are making a mistake. We are making a computation error, and this computation error will be accumulated after a few minutes or maybe hours according to the step size and the speed of the rotation speed. The error can be so big that we have to recalibrate the attitude using other means, not only accumulating small steps of rotations. Okay, but in any case, we have to take a decision which first. We have these 3 axes. And then we can take randomly, let's say first I will accumulate the rotations in X, then Y, and Z, or we can say Y, Z, X, or whenever you want. In any case, you are going to accumulate an error. The error will be different. But there is a standard how to do that. And this standard minimizes the difference between one computation and the other computation. The computation of one aeroplane will be similar to the computations of the next aeroplane. But remember, after a while, we have to recalibrate because we're accumulating an error. Okay, the standard says RPY, so roll, pitch, yaw. You remember, yaw are rotations in this direction, so we are rotating on this axis. Pitch are rotating in this direction, so rotating on this axis. Unroll is rotating here in this axis, so are these rotations. So the standard says first comes to the right, so this will be yaw here. That is the Z axis. The next will be the pitch. That is the Y axis. And last will be the roll. That is the X axis. So this is the standard how we should accumulate or micro integrate the rotations. So everybody is going to have the same minimal error. Okay, I said before, when we are rotating, we have a small problem that the axes are changing. Here I can show this graphically. Okay, first we rotate in X. This is our axis X. I will take this. Okay, this. Remember, I am using yellow because I cannot use green in this green screen I have here. Okay, then take a look. First we rotate in Z. Then we are changing the orientation of these both axes, as you can see here. We rotate Z in this direction, and then this was the original axis. That is the new X, and that is the new Y. Okay, next we rotate in Y. I'm going to take here, and then we are rotating so. Then I change the old Z to be now here, and now X has already 2 rotations. The first one comes here, and then the next one, I am rotating here in other direction, comes here. And now this is the new X. And now I am rotating by X. I'm take here, and then the other 2 are moving. So at the end, each axis will accumulate 2 movements, one from each other axis. As you can see here, this was the first axis movement from Y, and then the axis, the movement for X. and exactly something similar in any of these axes. So here we are having small deviations, and therefore the error will be small. If we have very big deviations, then the error will be very big. Therefore, we have to have a very high frequency when integrated rotations. Okay. Here I have an example. I have an aeroplane, and in this aeroplane I have the three axes which we are going to use with the corresponding color. X is red, Y is green, and Z is blue. And this correspond to yaw, this correspond to pitch, and this correspond to roll or bank. Okay, and this is our standard. This is the axis we are going to use in aeroplanes, and this is the colors we are going to use for all our axes. But here be aware, Z is pointing down, X is pointing to the front, and Y is pointing to the right. Maybe you will expect X shall point to the top, but in aeroplanes is pointing to the bottom. It's due to calculation rotation in positive angle. So positive angle will be like this and like this. Therefore, this is the definition of the axis in aeroplanes. Okay. Oh, now I'm going to show you what I showed you before with the paper aeroplane, two rotations in two different sequences. Here I'm rotating first pitch in X, and then I'm rotating yaw in Z. Then that was my original position. The red is looking to you, and this will be the final position after these rotations. Then take your paper aeroplane and do it by yourself. You will see. Okay, then I have two rotors. I will say the rotor, the first rotor, the first rotors come to the right. The first rotor is rotating in X, in Y. So this is the rotor on this axis. And then I multiply. Do you remember? When adding other integrating rotations, we do not add, we multiply. And we have to define the multiplication operator for rotors. Okay, and then we rotate with this rotor, 0, 0, 1. That is Z. Okay, this rotor is missing the angle. I am saying only which axis I am using. So I shall add here 90 degrees. Okay. Now let's do in other sequence, first yaw. So this will be the first rotor in yaw. And then in pitch. This will be the rotor in pitch. As you can see, the final position will be different. The start position is the same, but the final position is different. Okay, now how to accumulate this? I would like to do this rotation at the same time. So I have these two axes. Then maybe you will imagine, okay, the rotation axis, if I do these two transformations at the same time, will be 0, 1, 1. And that's right. Okay, then let's take this 0, 1, 1. And let's rotate. I will show later the angle which we are rotating. And then I make here a new hole, and I make this new rotations axis, which is 1, 1. Sorry, it shall be here. I made a mistake when building this aeroplane. Okay, and then I keep this and I rotate around this axis, and the result will be this. This is the real rotation. So if I will make it parallel, I am doing it parallel. Therefore, you see, it's better to find the real rotations axis and rotate on this axis and not first on X and then on Y. You are accumulating an error. Here, if you find the real rotations axis, then your accumulated error will be much more lower. Okay, and here I have another rotations vector. Let's say I'm rotating 3 times in all 3 axes. Then what I shall use is, for example, this rotation vector. And then I'm rotating, in this case, 150 degrees. And then this is the accumulation of 3 rotations, but using the direct axis which I am using. If the axis is, 1, 1, 1, it means it was the same rotation angle in all X, Y, and Z. If it will be different, one more, one less, and something like this, then the values will be different. So the one which is rotating faster will be the bigger number. The one which is rotating slower is the slower the smaller number. So if one axis is not rotating, then I will find at this position a 0, for example. And now let's see an example of rotations. Let's take my model or an CubeSat. And now I have a small problem. And here I have the three colors, red, blue, and green. But as you remember, green is my background, so my graphic program is removing all greens and it will be black. But think this is green, yes? Okay, now let's see how to permutate the axis. Here I have the three axes, what I mentioned before. And a permutation on axis will be, for example, this will be permutated with this. This will be permutated with this, and so on. Or I can permutate all three axes or all four axes. Let's see in an example with the cube. Let's begin with this attitude. Red is looking to you, then I have blue, and at the back I have red again, okay? And something similar here with the green. Okay, I'm going to take this initial position. I'm going to rotate by one axis. Let's say this axis. Let's define this axis is Y. Then to permutate, I have to make 90 degrees. I have permutated two axes, again 90 degrees and a 90 degrees. And if I do it 4 times, it will be at the beginning of the original position. Let's take another axis. Let's take the axis 1, 1, 1. So it will be from this corner to this corner. And then I am going to rotate until I have a permutation. Here I have my permutation. So you might ask, what was the angle which I rotated here? I'm going to rotate it again. And I have interchange again. And rotate again. And I have my original position. So you can imagine the steps of these rotations. We have three rotations. Three rotations, and at the end I have my original position. So each rotation has 360 degrees divided by 3. So 120 degrees. So every 120 degrees I am interchanging, permutating rotations axis. And now let's do it with this other. Okay, remember, with only one vector, x, for example, in this case, I am rotating in every permutation 90 degrees. With this axis, every permutation 120 degrees. And now let's take this axis, 110. 110 will be, for example, from here to here. I'm going to do it in the center of gravity, not here. Here will be difficult to rotate, but here. Now I am not going from corner to corner, I'm going just from here to here. And then I'm rotating here. Let's see. I begin with blue looking to you. I rotate. This is the blue on the other side. And I rotate again. That is again the blue on the front. Okay, then you see, with this axis, every 180 degrees, I am permutating some rotations axis or some axis of the system. Okay, then I could say, in this case, 90 degrees rotation in this angle, plus this plus is not adding. 90 degrees rotation in this angle is the same like 120 degrees in this axis. Okay, how to compute this? This is a little bit more difficult. Just remember how we are playing with angles and with axis, rotations axis. Okay. And now how to represent an angle. Okay, we have 4 different ways to represent angles, but we are going to select only 1 or 2 maybe. First, polar coordinates, you know, you saying 20 degrees to the left or 20 degrees to the right. But what we are using is Cartesian system. So we have a 2-dimensional plane and the position of a vector with 2 components, x and y. And if this vector has a length of 1, this x and y will define the angle of this vector relative to, let's say, x. We can do something very similar, but instead of having a 2-dimensional plane, we have a complex plane. And this complex plane had 2 dimensions. One is the real numbers and one is the imaginary numbers. So it looks almost exactly the same like Cartesian. But the mathematical operations are somehow different because we have an I imaginary component. And the last way how to represent vectors is a complex plane, and we use E power to the x times E. E is again imaginary number, the imaginary number E, I. Okay, and this operation produces a complex number, and this complex number is a vector in a complex plane like this. We are going to show this later. Okay, let's take this example. This angle can be represented just by telling this angle, or the coordinates of x and y. Here I have different representations of different angles which you are going to use. But let's take only 45 degrees an example. Okay, then you can see here 45 degrees can be represented by 2x and y. They are the same. Root from 2 divided by 2 and root by 2 divided by 2. The length of this vector shall be 1 because this has a length and radius of 1. Okay? And now we can represent this like a two-dimensional elements or adding a real number and imaginary number. Let's say root of 2 divided by 2 plus root of 2 divided by 2 multiplied by I. It's almost the same, but it has a nice thing for multiplications. Oops, I hope you can see the vectors. They are very weak. Okay. Okay, now you can see it better, huh? Now you can see the lines. Okay. I just wanted to show how nice it is to use complex numbers to compute rotations if you compare with normal Cartesian coordinates. We will use these complex numbers later when we are dealing with quaternions. But now just remember the name quaternions. It will come later. If you take a look to your math book, then you will see how to add sinus and cosinus to angles. For example, if you are handled with cosinus, which is, for example, the x coordinate, or sinus, which is handled the y coordinate from a number, okay, then you will see the cosinus of the sum of the numbers is this expression, which is very complex. And cosinus and sinus take a lot of computation time. Or the sinus of this of the sum of two angles will be these complex equations. Maybe we can do it easier. And this is the solution using complex numbers. Okay, we are going to represent any angle as the sum from a real number and an imaginary number with a length of 1. Okay, let's assume then an angle from 0 will be this point. This will be 1. An angle from 90 degrees, that will be plus I. This will be 90 degrees. From 180 degrees, that will be minus 1. From 270 degrees, that will be minus I. Okay, and then just multiply. Assume you want to have a 90 degrees plus 90 degrees. The solution shall be 180 degrees. Okay, then you multiply the two angles you have, I times I. And you remember, if you multiply I times I, you will get minus 1. And this will be this. Or let's assume you want to have this 90 degrees and rotate on 180 degrees. So 180 degrees is minus 1. Then you multiply I times minus 1, and then you will get minus 1. And you can see this is adding a rotation of 90 degrees plus a rotation of 180 degrees. So you are going to do that. And now let's try, for example, the rotation of 90 degrees plus 0. Then this will be this 1 times I. And then you will be here. And this is 90 degrees. Okay, and now let's try, does it works with other numbers? For example, let's use a simple example, 45 degrees. And you remember 45 degrees will be 1 plus I. And then normalize. We want that all vectors are normalized. But at the moment, let's forget the normalizing. At the end, we divide again by the length of the vector, and then we are going to normalize. So let's take 45 degrees is 1 plus I. And now let's multiply, or let's add 2 times 45 degrees. And if you have 45 degrees and add 45 degrees again, then you shall have 90, which is I. And here I have the multiplication. You can see it's just a second, 45 plus 35, that will be 1 plus I. Let's forget about the normalizing, yes, for the moment. Multiply by, again, the same, 1 plus I. If we multiply this, this will be 1 times 1 is 1. I times I minus 1. 1 times I, and again 1 times I. If you add everything, it will be 2I. Okay, and then you normalize, you divide by 2, and then you have I. And I is 90 degrees, so it works. Okay, and now let's try 90 degrees plus 45 degrees. The result shall be somewhere here. And this is the example 1 plus I plus I, which is 90 degrees, plus 1 plus I. This. The normalizing, let's do it later, yes? Then the result will be I times 1 is 1, times I is minus 1, and then you have I minus 1. And this will be I minus 1 will be somewhere here. And you can see this is 45 degrees plus 90 degrees. Okay, and this you can do all these angle operations just by multiplying. You don't need these complex expressions using sinus and cosinus and all of this. But now we have a small problem. This works only on one plane. So we are rotating only in one dimension. We have only one rotation axis to compute this, one rotation point. You will need, you remember we are living in a three-dimensional world, so we have to do it in 3 dimensions. Okay, then what we have is 3 imaginary planes, 3 complex planes. And we are going to call them the I plane, the J plane, and the K plane. Each of these is an imaginary number, so if you make the square of each of these, the result will be minus 1. But there are another characteristics which we will see later. So we are going from a complex plane to 3 complex planes, which are all orthogonal to each other, and then we can handle rotations just by multiplication of complex numbers. But this will come in the chapter quaternions later. Okay. The last way to represent the angles, what I wanted to mention is a whole to the power of xi. This is a complex number, so we are again in a complex plane. This x will be the contour if you go from here to here. So if you have this contour and multiply by I and then use as exponent to e, then you will get a complex number which has these 2 components, this component and this component. And so you can represent the angle just by the length of this contour. And for example, this contour from here to here, do you remember it will be P from here to here. So if you make a power P I, you will get minus 1, a very famous formula. So you know why. Okay, this is a very interesting way to represent angles, and this is if we need to represent the rotations of rotating machines, oscillations, or on all of this. But at the moment, we don't need it to compute of attitude, but maybe when you are dealing with control and you are dealing with oscillations, you will find this formula again, because it's ideal to be rotating around this circle, and you have to add only one more parameter, and that is time. Here you have time times x times I, and then you have a periodic function. Okay, but as I said before, you don't need it for rotations, you need it for control. Okay, then this in the alternatives we have to make our computations and represent angles. We have polar coordinates, we have Cartesian coordinates, we have the complex plane, and we have the Euler formula. I forgot to say this is the Euler formula. Okay, and we have the Euler formula too. Okay, our decision, we are going to select now just Cartesian, the Cartesian methods. Later, when we are dealing with quaternions, we are going to deal the complex plane. And how to represent the positions for translations, the pose. We have the Cartesian, cylindrical, and polar coordinate systems. We are going to use Cartesian systems. And for the calculations, we can use sequence of roll pitch yaw, which I do not recommend for computations. It works only for very small deviations. Or we can rotate about x, y, and z. This is the case if we are working with matrices, or we can rotate around one vector. That is the case if we are working with quaternions, for example. And we are going to work with these two methods. Okay, or calculations on the plane. But okay, our solutions is for calculations we use matrices with 3 axes, quaternions on one axis, which can be arbitrary. We use Cartesian coordinate systems, and the representation of angles will be Cartesian too. Okay, this is our solution, what we are going to use. Now, let's talk about rotations. We have 2 ways to think in rotations. What I have mentioned already is we have an axis. In this case, for the aeroplane, we have the 3 axes, and we can rotate around one axis. What I showed before, we have one axis, and then you can rotate around this axis, or here, or here. Okay. The other way how to think on rotations is on surfaces. Not around an axis like here, but you have a surface. For example, the ground plane here will be a surface, and I can rotate on this surface. So I rotate on this surface, which is the same if I am rotating in the orthogonal vector on this surface, pointing from the earth to the sky. Or I can rotate in this axis, or I can say I have here in the back a wall, and I can rotate on this wall. It will be the same. So some people prefer to think on axis, some people prefer to think on planes. And we have to learn how to go from one representation or way of thinking to the other way of thinking. Sometimes we are going to rotate on planes, sometimes we are going to rotate around an axis. Okay, here let's combine both of them. I am rotating from this vector through this vector. So I could say I have this plane and I am rotating on this plane. Or I can find the orthogonal vector to both of them, and then I can say I am going to rotate around this vector from here to here. Okay, and then I need 2 vectors. And with 2 vectors, I can define a plane in a 3-dimensional space. For example, I can place, just a second please. Okay, I can place these 2 vectors anywhere in space, and it doesn't matter, you will find a plane between these 2 vectors. So with these 2 vectors, I can define a plane. Now the plane is here, now the plane is here. Let's do it with a sheet of paper. So if I define these 2 vectors here, the plane will be here. So you can define a plane as function of 2 vectors. And then if you have these 2 vectors, you can make the vector product or cross product of one of them, and then you are going to get an orthogonal vector to both of them. So if you multiply these vectors, whenever they are in space, then you will get an orthogonal vector. And this orthogonal vector for the multiplication of this will be the rotation axis when going, for example, from this vector to this vector. Okay. And this is what we are doing. Then we see how we can rotate on the plane using 2 vectors, or the cross product of the 2, and then we have the axis how to rotate there. Okay, and now we have 2 different situations. This plane, the rotation plane, could be exact one of these planes of our coordinate system. And then we rotate first on this plane, or around this axis, then on this plane around this axis, and then on this plane around this axis. Or we can find the arbitrary plane, which is not aligned to this. It can have any attitude here on this reference system, and then we can find here the orthogonal vector to rotate directly from this vector, for example, from this vector to this vector, and we don't have to be aligned to this coordinate system. So we can have an arbitrary position of this plane and direction of the normal vector, which is the cross product of the two. We have only a small problem. I said before, we can define a plane with two vectors anywhere. But there is a restriction. These two vectors shall not be collinear. Collinear are, for example, if they are looking in the same direction or in opposite directions. But this case, they are collinear. If we have this case, here is clear how to define the plane, but here, how to define the plane. The plane between two of these vectors can be anywhere around this. For example, here I have these two vectors, and this plane will be a guilty plane, and these two. And the rotations will be totally different. So we have a problem if the vectors are collinear. For example, you are going in this direction, and then you are flying back. The result will be different if you rotate on this plane. For example, then you will rotate 180 degrees like this. Or if you rotate on this plane, then you will rotate 180 degrees like this. Or if you rotate in intermediary plane, then you will have another angle. Okay, then it's not clear defined how to rotate if we have collinear vectors. So we have to do an exception when dealing with this. Therefore, in some operations you will find we will be working with half angles and not with whole angles. And exactly the same, okay, you could say this is the planes, but we can use a rotation vector, and this will be the cross product of them. And now, if you took a look to your mathematics, you will see the cross product of two collinear vectors is 0, the vector 0, 0, 0. And where is the vector 0, 0, 0? It can be anywhere, so you can rotate in any direction. So it's not better. Okay, then warning with the collinear vectors. And here, a summary how to find the rotation axis and the angle where we want to rotate. And here you have to remember your mathematics from the school, and you remember the cross product of two vectors will be the an orthogonal vector to this, and this is the rotation axis, what we saw before. In this case, I said it's not permutative, so we have to know what comes first and what comes to later. For example, if I am rotating from here to here, then this comes to the right and this comes to the left. So if I am rotating from V to W, then my operation will be to the right, the older, and to the left, the newer, in this direction. If we interchange this, then I am rotating back. I am rotating from V to W, and I hope you remember the result will be inverse. This vector is A, and this vector will be minus A. You can try it with simple vectors, 1, 0, 0 and 0, 0, 1. You will see some, in one direction you get 0, 0, 0, 0, 1, and the other direction you will get 0, 0, minus 1. Okay, something like this. Okay, so we define the rotation axis. And what about the rotation angle? And maybe you remember the vector, the scalar product or dot product of two vectors will be the cosinus of the angle between two vectors. So we have defined both. We have defined the rotation axis and the cosinus of the angle. And here, this cosinus will be the same if you interchange these two values. So it doesn't matter which is left, which is right. The cosinus will be the same. And if you take a look to this, you will see cosinus is a symmetric function. So it doesn't matter if you rotate in minus or in plus, the result of the cosinus will be the same. This and this is the same. So the only way to represent positive or negative rotations is using the rotation axis, not using the cosinus. No help. And here we have another problem. If we rotate from 0 to 360 degrees, you will see it's ambiguous. Because from here to here, you can have two different representations for the same value. For example, here and here, this cosinus value can have this representation, this angle on this angle. So This is another reason why we shall not work with numbers from 0 to 360. We work only with numbers from 0 to 118. And from here to here, it's unambiguous. So in this case, we can represent these rotation numbers. But this comes later. At the moment, just remember how to represent the rotation axis and the rotation's angle. Okay. Here an example. I have these two vectors. And I said before, we want to have everything normalized. If they are not normalized, when we are multiplying rotors, we are changing the shape of our device, what we don't want. The device shall not change its shape or grow or shrink according to rotation. So always normalized, so we have always the length of 1. Okay, the cosinus of this will be the scalar product of these two vectors, normalized, of course. That is the length of one vector, and this is the length of the second vector. And how this scalar product works? The first two coordinates multiply, plus the sum, plus the multiplication of the second coordinates multiply, plus the multiplication of the third coordinates. And this is the cosinus of the angle from V to V. Okay, and now the cross product. You have these two vectors, and how to multiply these vectors. I hope you remember. You write 2 times. Well, there are 2 different methods. This is what I learned in the school. Others learned to write this on the other side and multiply 3 times. Okay, it doesn't matter. But that is how I learned in the school. This times this minus this times this, and this will be the first element of the vector. Then the second, this times this minus this times this, that will be the second, and the third one in similar way. Okay, let's make an experiment. Let's rotate from 1, 0, 0 to 0, 1, 0. Okay, the cosinus from here to here. Maybe you can see I am rotating from x. Wait a minute. Let's do it like this. Okay, I am rotating from x to y. Then you can see, I think this is something you can see, the angle from here to here is 90 degrees. And I think you can see, and the rotation axis will be Z. I think in this case it's easy to see. Okay, then the cosinus will be 1 times 0 is 0, plus 0 times 1 is 0, plus 0 times 0 is 0. Okay, and the cosinus from 0, where do I have the graph? Here you can see the cosinus of 0 is here, is 90 degrees. Okay, then as expected, the rotation from here to here is 90 degrees. And now let's find the axis. Okay, I take this here, 1, 0, 0, and then 1, 0, 0 again, and this here, 1, 0, 1, and 1, 0, 1, and then I multiply this, 0, 0. The second, 0, 0, and the third, 1 minus 0. Okay, and now take a look to this and tell me, it is right? It was as expected. I am rotating from here to here and I got Z. But is this right or not? Take a look. It is wrong. Do you know why? I took here on this side and this on this side. And I say the older vector come to the left and the newer vector, to the right, and the newer vector to the left. So this vector shall be here and this vector shall be here. What I am representing here is the rotation from here to here. Okay? So the reality shall be 0, 0, minus 1. Okay. Now, how to rotate? Which axis shall I take to rotate? I said, if I am rotating from here to here, I get this axis as rotation axis. It's only partially true. It's true, this is rotation axis, but it is not the only way to rotate. It is the shortest way. From here to here, if I am rotate about this is the shortest way to go from here to here. But I could have another rotation axis. For example, this. I can rotate like this. So there are at least 2 rotation axes. And we could ask if there are at least 2, maybe there are more. Okay, I can rotate on this axis. I can rotate on this other axis, I can rotate on this, or I can rotate on this, and the result will be the same. Only the angle which I am rotating is different. This is the shortest way, the orthogonal value, and this is the longest way, 180 degrees, going from here to here. Okay, if I have at least 4 rotations, possible rotations angles, maybe you will think we could have more. When it is true, all rotations axes defined by this plane here to this, these are the 2 vectors from here to here. So these 2 vectors define a plane. On any vector on this plane can rotate vector A to B or B to A, how I defined it here. Okay? Well, then how to define all these vectors? We say we have this vector here, this is this here, and this vector here, that is this here. And then I define a plane. On any vector on this plane can rotate this from here to here. And this plane can be defined by to this vector or only, let's say, this orthogonal vector to this plane. Can you see what is this, the orthogonal? This orthogonal is just A minus B. A minus B with this vector. But if you translate to this 0 position, then it will be this vector. Okay, how to define these 3 vectors? This vector will be the cross product of A and B. And this is in the middle. So it will be A plus B divided by 2, the center vector. Okay, then we can define this plane by the cross product of this times this. And this will be this vector, which is orthogonal to this or this. Or much more simple, what I said before, A minus B. It will be the same. So I can use any rotation in this plane. And you remember what I said, if I have any vector on a plane, the rotations will be like this, or like this, or like this, so I can have different results. And the reason is, to have a clear defined rotation, I need at least 2 vectors. I'm going to show in an example, just a second. Let's say I have this structure, and I am using only this vector. I am going to define the direction of this vector, and the define is it's pointing to you. But even if I rotate around this vector, this will still be pointing to you, but I have another attitude. Do you see? I have to define at least 2 vectors. This is pointing to you, and this is pointing to the ground. And then I have a fixed, well-defined attitude. Okay, in this case, we have to do the same. For a rotation, we have to define 2 vectors. Before the rotation, these 2 vectors, for example, and after the rotation, these 2 vectors, for example. And then with these 2 vectors, I have a well-defined rotation, and I have no degree of freedom to say it could be like this or this, etc. Okay, then let's come back and see how to define this with 2 vectors. Okay, here I have only from vector A to A. Now, let's use 2 vectors. Okay, I want to rotate from A to new A and from B to new B. A apostrophe and B apostrophe. For this vector, for these rotations, I can use any vector on this plane. And for the rotation from this vector to this vector, I can use any vector on this plane. And what I need is to find one vector which is in both planes at the same time. And this is the vector which will translate at the same time B to B apostrophe and A to A apostrophe, because this vector is in both planes. And this is the only one which will make this with those 2 vectors at the same time. Okay, how to define this? Do you remember the definition of this plane is the orthogonal to A minus A, AA minus A apostrophe. And exactly the same, the plane for B is B minus B apostrophe. And then I want to find one which is orthogonal to this and one which is orthogonal to the plane of B. Do you know how can I find one which is orthogonal to D? Can be any one on this plane. And at the same time, orthogonal to the plane for B is the cross product of these 2 vectors. And then I will find a vector which is orthogonal to this and orthogonal to the other plane which I require to rotate B. Okay, the result is this will be A minus A apostrophe, and the other will be B minus B apostrophe. And the cross product of this will produce the vector which I have to use to transform at the same time this to A apostrophe and B to B apostrophe. It's clear, huh? Okay. Another way to represent, to find the right rotations, maybe you remember at the beginning we said, okay, let's do something like this. At the beginning it seems why to make this extra complexity? We don't need it. We said, okay, a point can be defined by 3 scalars multiplied by 3 vectors. And the 3 vectors are defined, the vector for x, which is 1, 0, 0, the vector for y, which is 0, 1, 0, and the vector for z, which is 0, 0, 1. If I multiply the first scalar times this, plus the second scalar times this, plus the third scalar times this, I get a vector which looks like this. And then you say, what for then? I don't need to come to the same place. I don't need to do that. But now it comes. These vectors are, for example, sorry, this is green. For you, it's black. Okay. Let's say this is our reference coordinate system. And this is our body coordinate system. And at the beginning, these are the definition of the x, epsilon, and y. This is here, this is here, and this is here. It's clear. But if you rotate, then you will have another vector for x, another vector for y, and another vector for z. The point is rotating together with your body. So the position of your point relative to the body is the same, but relative to this will be different. To find the position relative to x, you multiply by this, your own x vector. The relative position to the y vector of the reference, you multiply by the y vector, and the same with the z vector. Okay, now you can see why do we need this, because it will not stay like 1, 0, 0, but it will change. All of them will change. Let's take an example. Okay, I say my reference system has these 3 vectors, A, B, and C. Oh, I think you cannot see these white lines, which says this is my reference coordinate system, and these are the coordinates of these 3 vectors relative to my reference coordinate system. Okay, at the beginning, the vector x is this, y is this, and z is this, so I can create a matrix. This is the first vector, the second vector, and the third vector, and this matrix will be my rotation relative to my reference coordinate system. Okay, now let's see. I am rotating from here to here. Then these are not anymore 0, 0, 1, but they have other coordinates. They are looking now in other direction. So I represent here the attitude here, and here the attitude here. And remember, this vector corresponds my x vector relative to my reference coordinate system. This vector represents the y vector relative to this, and the same with the z vector. So before the rotation and after the rotation. And now I would like to know how to come from here to here. If I have this coordinate system before and this, not coordinate system, this attitude before and this attitude after. Okay. And now you might say, okay, now we have 3 vectors. You see, 3 vectors. And I said before, actually, we need only 2 vectors to have a well-defined rotation. I am mentioning now 3. Is this true? Do we need 3? Or do you think 2 will be enough? What do you think? 2 will be enough. Remember, they are orthogonal vectors, and if they are orthogonal vectors, I can find the third one only by a multiplication of these 2. So actually I need only 2 vectors. For example, I and y, and I can compute z as the cross product of these 2. Or I can have only y and z, and I can find x, or whenever you want, any permutation you want. So actually, it's not a problem. It's true. I need only 2 vectors. and the third vectors can be computed, so it's not a problem. But if we are using a coordinate systems like this, then we have all three vectors, so let's use them. Okay, to define a rotation from here to here, let's call this A and this B. We can generate what we call the direction cosinus matrix. And the direction cosinus matrix is defined as follows. Remember, if you multiply two vectors scalar, then you will get the cosinus when going from A to B, which is the same cosinus going from B vector to A vector. These are vectors, do not forget. Okay, then we have AX, which is a vector, times BX, which is a vector. That is the definition of the vector X for A, and this is the definition of the vector X for B. Okay, and this will be at this point. And we do the same AX times BY, so we multiply das times this, we'll get this position, then this times this, the second position, this times this, the third position. And for the next row, we use this with AY times this, and then this, and so on. But please keep in mind, each of these is a three-dimensional vector, and therefore you can do this scalar product, and then you get the cosinus. So you have a matrix of cosinus going from any vector to any vector in any permutation. Or let's do it in a different way, but exactly the same. We say this was our original position, the original x vector, and this was the x vector after the rotation. So I multiply the x vector before the rotation times the x vector after the rotation, and I get this cosinus. And the same with x and y and x and z, and then all these permutations. So before and after, maybe easier to see than this. Okay, and then you get this cosinus matrix. How it works. Let's say, do you remember what I say how to do this? This times this, and then this times this, and you will see this looks like a vector multiplication. It is a vector multiplication. If you multiply this vector times this vector, then you get a matrix. 3 times 3. But there is a small thing. Each element here is a vector by itself, but it shall make no difference. It's the same method which we are using. Okay, then you have this matrix multiplied by this matrix transpose before and after, and then you will get this cosinus directions cosinus matrix. And now let's see how it works. An example with a rotation. Okay, this is what I define. This is our starting position, and I generate this. Okay, now let's take this point P. And this point P is relative to this coordinate system, x, y, and z, which is here. But if I want to know the position of P in the reference system, then I have to multiply this P by the definition of x, y, and z in my own body coordinate system. So P will have these coordinates in the reference coordinate system. If we want the opposite, if I have the position in the reference coordinate system and I want the position in my body coordinate system, then I multiply the per ref divided by this matrix. Use algebra. And the division by this matrix is the inverse of this matrix, -1, and this will be P. And there is something special. If these elements are all orthogonal, these vectors are orthogonal, then you will see the inverse of the matrix is the same of the transposition of the matrix. So if you have like this, you make like this, and this will be the inverse. Or if you have like this, you make like this, and then it will be the inverse. That is the transposition. And if they are orthogonal, this is the inverse matrix. Okay, then let's see. This is clear in both directions, I hope. Okay, and now after the rotation. This was before the rotation. And after the rotation, the position keeps still the same coordinates in the body frame. It didn't deform. But the x, y, and z vectors, they have another orientation, they have moved. Then you multiply this point times this matrix which defines your new attitude, and then you get the position of this point after the rotation. You rotate from here to here. Well, here I have a translation too. The translation can be used added or subtracted. That's not a problem. Okay. And now let's see. Per ref is after the rotation. P, and P is this, times the rotation, the main coordinate system after the rotation. So the original P is this. It's clear, yes? Times the orientation of your body after the rotation. And remember, this -1 means transposition, then you rotate from here to here. So you have this vector is this times PA. P reference before the reference. And then you have the point after the rotation, the point before the rotation multiplied by this matrix. And this matrix is this, what we have here. Okay, you see? And so it's the way how we generate this cosinus direction matrix. How to rotate if we know the orientation of my 3 element coordinates vectors before and after the rotation. Okay, and this is with rotations matrices. Now let's continue with more details about rotations matrix and quaternions, which I said with 3 orthogonal complex planes. And then I'm going to mention something about the Euler angles, which we are going to use only for very small deviations or for the representation of attitude or to read the measurements of our rotation device. Okay, then see you in the next movie. Thank you very much.